Welcome back to the lecture series of network theory, where we have already started gaining the knowledge on sinusoidal steady-state response of RLC network. And as I promised that after RL circuit, I will be covering the concept of RC circuits. So first in today's class, I will discuss about series RC circuit, and then in the following class, I will discuss about parallel RC circuit, and then series RLC circuit and parallel RLC circuit. So let's start the class. First, we will start with a purely capacitive circuit. Now in this circuit, as we can see, where we have a single capacitor and that is energized by an AC voltage which is sinusoidal in nature. Let's assume that this AC voltage is supplying an AC current which is I. Now this small v and small I are basically, they represent the instantaneous values of voltage and current respectively. Now let's take voltage as a reference. So since this is AC voltage and this is sinusoidal in nature, so the small v will be written as Vm sin omega t, where Vm is the peak value or maximum value of the AC voltage that is applied across this capacitor, and sin omega t, where omega is the angular frequency which is measured in radian per second, and omega we know that is equal to 2 pi f, where f small f is the linear frequency and the unit of this linear frequency is hertz or cycles per second. This is a thing that we already know. And Vm sin omega t, this is the format of sinusoidal waveform. Next, we will find out the current that flows through this capacitor or through this circuit. Let's take this, or let's represent this current as IC. So we know that this current is how it is related to voltage, that is C dV dt, means the rate of change of the voltage drop across the plates of the capacitor, and that is multiplied by this capacitor. Now if we put the value of this instantaneous voltage here, then it will be C then d Vm sin omega t divided by dt, means the Vm sin omega t will be differentiated once with respect to time. Now if we differentiate this expression, so Vm is constant with respect to time, so Vm will come out of this differentiation, and sin omega t will become cos omega t, and since it is omega t, so this omega also will be multiplied with this factor or cos omega t. So finally we will be getting C Vm and omega. This is the rule of differentiation, so I don't need to explain that much, and cos omega t. Since this is the expression of current, so Vm multiplied by omega and C, this whole thing will give us a measurement of current. So let's assume that as the maximum current, or Im, and cos omega t. Now since we are here, the voltage that we applied was sinusoidal in nature, so it will be expressed in terms of sinusoidal wave or signal. So by the rule of trigonometry, we can write cos omega t as sin omega t plus 90 degree. So 90 degree plus omega t, that will give us cos omega t, and 90 degree plus omega t, that means it lies in the sinusoidal, this angle lies in the second quadrant where the sine is positive. And since the voltage was maximum voltage, accordingly the current we have also taken here the maximum current. Now I see the current through that capacitor or through that circuit. Now we are getting this expression for IC. So Im, as I said, this is the peak value of the AC current flown through that capacitor. Now from this expression of IC, the 2 points we can conclude. The first one is that Vm, here omega C Vm we assumed as Im, so Vm will be equal to Im divided by omega C. Omega C Vm is equal to Im, so Vm will be Im divided by omega C. Now between voltage and current, as per Ohm's law, how they are related, that voltage is equal to current multiplied by the resistance of that path, or if it is an AC circuit, then impedance of that path, or if it is purely AC component, then the reactance of that AC component. So since it is a purely it is only a single capacitor that we use, that means only AC component we have used here. So here instead of resistance or impedance, we will only use the reactance part of that capacitor or AC component. So here it will be capacitive reactance. So in place of 1 by omega c, if we put that capacitive reactance of that capacitor, then it is x suffix c multiplied by Im. That means we can say that the capacitive reactance of that capacitor will be equal to 1 by omega c. So this is one relationship that we can derive or we can conclude here from this expression or from this circuit. So xc, the capacitive reactance, will be 1 by omega c. And I have already discussed in one of my previous classes that the unit of reactance, whether it is inductive or capacitive, it is taken in ohm. Now the another relationship that we can develop from here, that since this the first relationship is between the maximum or peak value of voltage and current, so we know that RMS value, be it voltage or current, that is maximum value divided by root 2. So maximum value, now we can replace maximum value by RMS value multiplied by root 2. So in place of maximum value of voltage and current, if we replace those quantities by RMS value, then root 2 will get on both the sides of the equation and they will cancel each other. So in on both the sides of that equation, the RMS value of that voltage and current will remain. That means we can say that also the RMS value of the voltage and RMS value of the current, they are also related by this relationship, as they are related as the maximum value of the voltage and current related. And here also 1 by omega c is the measurement of capacitive reactance. So if one of the quantities or one of the values is known to us, be it voltage or current, then the other value can be easily found from this relationship. And another important point that we have to notice here, the voltage was taken as a reference and the expression of this instantaneous voltage was Vm sine omega t. And when we found out the current through that capacitor, we got this expression Im sine omega t plus 9. So here as we can see, this 90 degree is coming in the expression of the current, and that is plus 90 degrees. So this, as we know, this represents the phase difference between voltage and corresponding current. So here in this purely capacitive circuit, what we can conclude is the current leads voltage, corresponding voltage, by 90 degree or pi by 2. So that is another conclusion that we can draw for a purely capacitive circuit. So between voltage and corresponding current, the phase difference will be 90 degree, exactly 90 degree, and the current will lead voltage. So here, if this is the voltage, the applied voltage, then in anti-clockwise direction, this is the measurement of 90 degree, and this will be our instantaneous, the phasor of instantaneous current. Now if we draw the voltage phasor this way, then if we move anti-clockwise by 90 degree, so this will be the measured phasor of current. This angle is again 90 degree for purely capacitive circuit. But if it is not a purely capacitive circuit, that means if with capacitor, if we have a resistor or resistance value in series or maybe in parallel, phase difference between voltage and current will be no more 90 degree, rather it will be less than 90 degree. And since we are discussing about series RC circuit, so next we will see that how the phase difference is less than 90 degree. But before that, we will also see the voltage and current waveform in case of purely capacitive circuit. Now the waveform which is drawn in red, that represents the voltage, and here this point is the origin or is the intersection of x-axis and y-axis. So this is the 0, 0 point, and since voltage was taken as a reference, so we are starting voltage waveform from here. Along x-axis we have taken time or omega t, the angle, and along y-axis we have taken the amplitude of voltage and current. Now as we can see, from this point to this point, this voltage waveform is completing one cycle or the positive half cycle, and this point measure 3.14. We know that the relationship between radian and degree is pi radian is equal to 180 degree. So 3.14 radian will be equal to 180 degree. Now on this scale, X scale, basically we have taken the measurement of angle in radian. So here it is 3.14 means it is the measurement of 180 degree. Now from this point to this point we have the negative half cycle, and this point measures 6.28. That means from this 3.14 to 6.28 there is another 3.14 that measurement. So that is another pi radian or 180 degree. That means for the complete cycle of this sinusoidal waveform or voltage waveform, the angle measurement is 360 degree. Now here the blue line or dotted line represents the current, and from this point to this point if we move on the negative side, then we can see here that this is the measurement of, here it is 1.57 negative minus 1.57, because here we are moving on the negative side of omega t or times. This is 1.57. That means this is the measurement of 1.57 radian will be the measurement of pi by 2, that means 90 degree. So this, between this point and this point, the angular measurement is 90 degree or pi by 2, and this is the waveform of current. So from this waveform also we can see that the phase difference between voltage and corresponding current, here the voltage is starting and here the current is starting. So these are the corresponding points of voltage and current, and there the phase difference between these 2 points is 90 degree. And here when the voltage is at 0 value, means when the omega t value is 0 for voltage, we can see here the current is not 0, rather the current is maximum. Now if we compare the positive half cycles of voltage and current, we can see here that when omega t is equal to 0, when the voltage signal or waveform is just starting, by that at that moment the current has already reached at its peak, and the current is starting here. That means we can see from the waveform that current is starting before voltage. So in case of purely capacitive circuit, we can say that the current leads voltage, and it leads voltage by 90 degree. Next we will see a series RC circuit which is again energized by a sinusoidal AC voltage. Now here we have R and C resistor and capacitor connected in series, and that series connection is energized by this voltage. Here small v represents the instantaneous value of that voltage signal or waveform. The voltage if that supplies current I, where the small I represents the instantaneous current value. Now since this is a series circuit and current is the common factor here, the same current flows through resistor and capacitor. So here the current has been taken as a reference, and that too will be a sinusoidal AC current. So I will be represented by Im sin omega t, so instantaneous current. Now from or by the help of this expression of instantaneous current in this series RC circuit, next we will find out the voltage drop across this resistor, which we represent by VR, and across this capacitor, which we represent by V suffix C. So VR is the voltage drop across the resistor, so it will obey Ohm's law. It's simply current multiplied by the resistance of the resistor, so I multiplied by R. Now R is the instantaneous value, because at any moment we need to know what is the value of that current. So here instantaneous value has been used. So I will be replaced by this expression Im sin omega t, and that is multiplied by R. Next we will find out the instantaneous voltage drop across the capacitor. Now we know that the current which flows through the capacitor, that we have already seen in the previous slide, that is C multiplied by dv dt or dvc. Now from this relationship, if we want to find the voltage drop across the capacitor, then it can be done this way. The current value first will be divided by this capacitance of the capacitor C, then dVc will be written as IC by C, and then dt will be multiplied. Then if we integrate dVc and then IC divided by C dt, then 1 by C, since it is constant with respect to time, so it will come out of the integration, when finally we will be getting this expression where 1 by C, then integration IC dt. IC is the current flown through that capacitor, and this is this instantaneous current. So in place of IC, this expression of that instantaneous current has been written. So it is Im sine omega t, and that is integrated with respect to time. So dt. Now if we integrate from the rule of integration, we will be getting this factor. Im is constant with respect to time, so that will come out of the integration. Then Im by C, and from the rule of integration, this sine omega t will become minus cos omega t, and since this is omega t and we are differentiating with respect to time, so that omega will be divided, the cos omega t will be divided by omega. So finally we will be getting minus Im by C omega multiplied by cos omega t. Now since we are finding out the voltage drop across the capacitor, and that we want to represent in terms of the sinusoidal signal, so here cos omega t can be written as sine 90 degree minus omega t. That also can be written as 90 degree plus omega t, but since we have a negative sign outside, and if we take that inside, then that will make the angle minus 90 degree minus omega t. But since we in the general expression of the sinusoidal signal, we have positive omega t, to match with that format we are using this relationship 90 degree minus omega t, so that when further we will take this negative sign inside, then it will become minus 90 degree, and this omega t or minus omega t now will become positive omega t plus omega t. So this will become sine omega t minus 90 degree. So this is Im by omega c or c omega sine omega t minus 90 degree, and this is an expression of sinusoidal signal. Now this is an expression of voltage signal, and we know that voltage in case of a series RC circuit, it will be the current which flows through that series RC circuit multiplied by the impedance of that series path. Now from this relationship, what we can conclude here is, since this is the voltage drop across the capacitor, now here we are considering only the capacitor. So the voltage will be related to the current by its reactance value or capacitive reactance. So we can say from here that this 1 by omega c will be the reactance of that capacitor. So Im divided by omega c can be represented as 1 by omega c will be capacitive reactance multiplied by the maximum current. So it will be finally the maximum voltage by Ohm's law. So maximum voltage, and this is an expression of voltage only, voltage drop, so that satisfies. So Vm and then sinusoidal the sine term. So this matches with the expression of the sinusoidal waveform. Now from the expression of Vr, we can see that it has exactly the format of this current, and there is no phase difference. It has only omega t, sine omega t. That means we can conclude here the current which flows through that resistance of that series branch, that current and the voltage drop across the resistance, they are in the same phase. There is no phase difference between these two quantities, this current and this voltage drop across the resistor. But if we compare this current, since this is a series circuit, so same current and the voltage drop across the capacitor, we can here see that the voltage is lagging by 90 degree. The voltage drop only across the capacitor, that is lagging by 90 degree. Now further, if we calculate the total instantaneous voltage drop across that series RC branch, then we can do this way. The voltage drop, this V will be summation of these two individual voltage drops, and that we can also prove by using or applying KVL here in this closed path. So small v, this will be equal to VR plus VC, So the supply voltage will be equal to the summation of this individual voltage drops. Now VR we have already found, and that is Rim sin omega t, and that's what has been written here. VC also we have already found, and that is Im by omega c and sin omega t minus 90 degree. So we are just simply adding these two values that we have already obtained. Now Rim sin omega t, let it be that value because it is already a sinusoidal, it has that expression or that nature, sinusoidal wave. Now we are expanding this sine term which has the format sine A minus B, and that we know it is sine A cos B minus cos A sine B. So here omega t is A and 90 degree is B. So it will be simply sine omega t cos 90 degree minus then this constant Im by omega c, then cos omega t sine 90 degree. And cos 90 degree we know that value is 0. So altogether this term will vanish. And sine omega t, that value is 1, we already know. So finally, the modified equation will be Rim sin omega t minus Im by omega c cos omega t. This sin 90 will become 1. Now, if we draw the phasor diagram, since I was taken as a reference, so let's draw I first, the phasor of I, and this is the phasor, suppose. Now we have seen that the voltage drop across this resistor is in the same phase with this supply, with this current or supply current. So here this will be the, if this is the phasor of VR, then I and VR will be in the same phase. That's why the parallel lines have been drawn here. There is no phase difference. And between I and VC, here we can see that the phase difference is 90 degree and VC is lagging I. Since minus 90 degrees, so voltage is lagging the corresponding current. So here the VC, if we draw VC, then it will give us a lagging voltage, and that will lag by 90 degrees. So this will be the measurement of VC. Now if we redraw VC here, the parallel line of VC, and if we take the resultant of these two vectors, then this will be the measurement of the instantaneous total voltage drop across that series branch. This will be the measurement of VC. This is VR, this is our VC, and their resultant will be the resultant voltage, that means the total instantaneous voltage across that series RC path. Now we can see from this phasor diagram that this V, that means this V, between this V and this I there is a phase difference, and that phase difference is no more 90 degree, rather it is less than 90 degree. Let's assume that value as theta, but still that is the total voltage or total instantaneous voltage across that series path is still lagging the corresponding current. So here, since we have a capacitor, so it will follow the capacitive nature, the nature of the capacitive circuit. So here also the voltage drop will lag the corresponding current, but this time since it is not a pure capacitor or the purely capacitive circuit, so the phase difference will be no more 90 degree, rather it will be less than 90 degree. So when we are writing the expression of instantaneous voltage, here we are expressing as Vm sin omega t minus theta. So Vm is the peak value of that voltage or total voltage drop across this RC branch, and then since it is sinusoidal in nature, so sine and omega t, and since this voltage is lagging the corresponding current by this angle theta that we assumed, and since it is lagging, so minus, so the expression of that instantaneous voltage will be this. Now if we expand this this sinusoidal term, so again it will follow this formula sine A minus V. So on the left side of this equation we will have Vm, which is constant term here, then sine omega t cos theta minus Vm cos omega t sine theta, and on the right side as the terms that we had it they will remain same. Now if we equate the like terms here, then on the left side we have sine omega t, on the right side also we have sine omega t. On the left side we have cos omega t, and on the right side also we have cos omega t. So in the next step we will separate them, and if we do that, then Vm sin omega t cos theta will be Rim sin omega t. So this Vm sin omega t cos theta will be equal to Rim sin omega t, and the cos omega t terms also we are separately writing here. So this will be from that equation, minus Vm cos omega t sin theta will be equal to minus Im by omega c cos omega t. Now if we equate the coefficients of like terms, means from this equation the like term is sin omega t, and from the second equation the like term is cos omega t. So if we equate the coefficients, then the relationship that we get from the first equation, it is Vm cos theta, and that will be equal to Rim, and from the second equation it is minus Vm sin theta, and that will be equal to minus Im by omega c. Minus minus will cancel each other, so it will be Vm sin theta Im by omega c. Now our next objective is to get the phase angle, means phase difference between voltage and corresponding current, then to get the impedance value of that series RC path, and then to represent the instantaneous current of that flows through that RC branch. Let's do that one step by step. So since sin theta and cos theta, these two values are known, so if we just divide these two terms on both the sides of both the equations, so from left, on the left side we will have this relationship Vm sin theta, and if we divide the left side of the first equation, then Vm cos theta. And similarly, if we divide the terms which we have on the right side of both the equations, then it will be Im by omega c, then divided by Rim. This Vm will cancel each other, this Im also will cancel each other. Then that means we are getting this relationship, tan theta will be equal to 1 by omega CR or R. So from here we can conclude that theta will be tan inverse 1 by omega CR. Now next is to find out the impedance value of that series branch. For getting that, what we are doing here, we are just taking the square value of both the terms of both the equations, and then we are adding them. So Vm cos square theta it will be, and then we will add that with Vm sin square theta. On the left side we will have Vm square cos square theta plus Vm square sin square theta, and since we are adding them, so Vm square is the common factor, so it will be taken out, or it will be taken as common. Then inside the bracket it will be cos square theta plus sin square theta, and we know that value is always 1. So that means after adding them on the left side of that equation, we will have only Vm square, and from the right side we will be having R square Im square, means Rim then square value plus Im by omega c, and then that square value. So we are adding these individual square values. So to get the value of Vm, peak voltage value, we are taking the square root of the addition of those two square terms. So from here we can what we can write is, since we can see that inside the bracket we have Im square, that term common, so if we take out from the square root, then square and then square root, so it will be Im only outside that square root, Im, and then inside that square root we have R square plus 1 by omega c square, and this is Vm, this is Im. That means whatever we have here in this expression, that will be the measurement of the impedance. Vm is the peak value of the voltage, Im is the peak value of the current, and they will be definitely related by Ohm's law. So it will be V will be equal to I multiplied by the impedance. So this will be, the whole thing will be the measurement of impedance. So the impedance of that series RC branch can be found this way. We know that impedance of a series RC circuit, it is written as R plus 1 by J omega C. Now we know that 1 by J, if we multiply the numerator and denominator by J, then it will be J divided by J square. So it will be J divided by J square, means J square itself is minus 1, so it will be finally minus J. That's why the impedance of a series RC path is written like R minus J multiplied by 1 by omega C. And this is the rectangular representation of a complex number, and if we convert this rectangular format to its equivalent polar format, then we know how it is done, because I have already discussed in one of my previous lectures. So it will be simply square root of the summation of the individual square values. So it is r square plus 1 by omega c square, and that we have already seen in the previous step. So this is the measurement of impedance, and then we will have the angle value. This is the r value and this is the theta value. So it is tan inverse. Theta will be the phase difference between voltage and current, and that we have already found. So this is the tan inverse 1 by omega cr. And when we will be solving numericals, then straightforward we can use the calculator or online calculator to convert from one format to another format. So this is the measurement of impedance. Now if we want to find out the maximum value of current that flows through that series RC branch, we can find from the maximum value of the corresponding voltage. So Im will be Vm by Z. Again, it is related by Ohm's law, and we use here the impedance instead of resistance or reactance. We are using the whole RC branch here. So Vm by Z, and since we know the Vm value because the voltage was taken as reference initially, and that was represented as a sinusoidal signal. So from that expression we can use the peak value. So Vm is known to us. So Vm by Z, and by now we have also found the impedance value, and that is r minus j multiplied by 1 by omega c, and this is rectangular. And since we are dividing Vm by a value which is represented in a rectangular format, so what we have to do is first we have to convert this rectangular into its corresponding polar format, and this is the value that we have already obtained in the previous step. Now Vm, since it is only Vm, so we can assume this as a polar format. This type of polar format, it will have Vm, then the angle will be 0 degree. So here in this expression of maximum current, we have two values in the numerator and denominator which are represented in polar format. Now we know the rule of division in case of AC components. So here the R value in the numerator means Vm will be simply divided by the R value of the denominator, which is this. So the final R value the real value will be this, and the angle wise this angle will be subtracted from the angle which we have in the numerator. It will be simply 0 minus this angle. So it will be minus tan inverse, since it is 0, so it will be minus tan inverse 1 by omega cr. Now from this negative sign also we can again conclude that the current is lagging the corresponding voltage in case of series RC circuit. Now till now we took the voltage as reference, and with respect to that we represented current. Now here to get the theta value, what we can do is, this is coming from this relationship. We know that tan theta is y by x. So here the relationship in the denominator is r minus j and then 1 by omega c. So that can be written as r plus j and minus 1 by omega c. So when we will find out tan theta, then it will be minus 1 by omega c divided by r. That means it will be minus of 1 by divided by 1 omega cr. So that means the angle that we will get, it will be minus tan inverse 1 by omega cr here. So it will be angle minus tan inverse 1 by omega cr. Now in the numerator we have 0 degree, and in the denominator we have minus tan inverse 1 by omega cr, a negative angle. And we know in case of polar division, or in case of division and between two polar values, the angles are simply subtracted. So it will be 0 minus minus tan inverse 1 by omega CR. So minus minus, finally it will be plus. So the angle of this current or maximum current, it will be plus tan inverse 1 by omega CR. So here we can see the current in the expression of current or maximum current, the angle that we are getting value wise, it is tan inverse 1 by omega CR, and it has a positive value, it is plus. That means the current, maximum current is leading the maximum voltage by this angle. That means this is the phase difference between current and voltage, and that we have already seen previously, that the current leads corresponding voltage in case of capacitive circuit. Now if we want to obtain the expression of instantaneous current in case of series RC branch, then that can be written like I, small I, it will be expressed by small I, and that will be Im sine omega t plus theta, since I leads voltage. So it is plus theta, and this is the measurement of the phase difference. Now this Im we have already obtained in the previous step, and this is the measurement of that Im, Vm divided by this much value. So in place of Im, here this value has been written, and we are not writing the angle separately, as that angle value we have, or the phase difference value we have incorporated inside the sinusoidal expression. So here sine omega t plus theta, in place of that theta we are writing this angle value, which is tan inverse 1 by omega CR. So this is the explanation of a series RC circuit. Now this we will again see in the form of voltage and current waveform. So here again the red waveform is the representation of voltage, and the blue or dotted line is the representation of current, and this is the point of intersection of x-axis and y-axis. This is the origin 0, 0 point, and since voltage was taken as a reference, so here the voltage signal is voltage signal is starting from this point, and this is the measurement of pi by 2, where the voltage is at peak, and radian wise this value is 1.57 radian, and this is the measurement of one complete cycle or positive cycle. This point is, the value is 3.14, and from this point to this point again that value is 3.14, or the abscissa of this point is 6.28. so for one complete cycle of the voltage, it is the measurement of 360 degree. Now on the left side of that voltage signal, what we can see is that current is starting at this point, and when the voltage is has zero value, the current has some other value which is not zero. Here the current is zero at some other point which is ahead of this voltage, and if we measure the difference between these 2 points, we can see here that this measurement is not 1.57, rather it is less than 1.57. 1.57 means it will be around at this point where it is at negative peak. So this will be 1.57 or minus 1.57, and this point is much less than that value. So that means from here also we can conclude the phase difference between voltage and corresponding current is less than 90 degree. But still, since this is capacitive circuit, so here current will lead the voltage.